Hello everyone, let's try to be a cheat code ninja today. This is a very interesting tree problem and we will be discussing two techniques which can be used commonly in many other tree problems. Let's look at the problem. We are given a binary tree and we have to find the maximum difference between the values of two nodes, and one of the nodes has to be the ancestor of the other one. And by ancestor we mean that the other node should be a part of the left or the right subtree of the ancestor. For example, 8 is the ancestor of all these nodes. Similarly, 10 is the ancestor of nodes 14 and 13. Similarly, 3 would be an ancestor of these nodes, and we could consider 3 and any of these nodes and find their absolute difference. For example, if we consider 3 and 7, the absolute difference would be 4, and we have to maximize this difference across all the nodes and their ancestors. For instance, if we compare 14 and 10, the difference will be 4. On the other hand, 10 is not an ancestor of 1 and 1 is not an ancestor of 10 because neither of them are part of a child subtree of the other. Similarly, 10 and 6 are not related in any way. Even two siblings, 1 and 6, whose parents are the same, are not the ancestors of one another. In the example, the difference between 8 and 1 is the maximum possible difference that is possible. Let's try to come up with an intuitive solution for this. Let's understand the base case where there is only one node in the tree. In this case, there are no other nodes to compare it with, so the difference of the node with itself would be 0. This means that our final answer will at least be 0. Because if there are other child nodes and they differ in value from our ancestor node, since we are taking the absolute difference, it would be at least greater than 0. The brute force way to solve this problem would be, we can initialize our result to be 0, and then for each node, we'll compare it with all the nodes in its subtree and keep track of the maximum difference we have found so far. Initially, we'll start at the root element 8. When we compare it with 10, the difference is 2. When we compare it with 14, the difference is 6, and it will be the new maximum difference we have seen so far. When we compare it with 13, the difference would be 5. It is less than the maximum difference we have seen, so we'll just continue. Similarly, we'll compare it with 3. The difference would be 5 and we won't update our maximum difference. Similarly, we'll compare it with 6. And when we compare it with 1, the difference would be 7. It would be the maximum difference we have seen so far. We'll repeat the same process for the ancestor node 10 and all of its subtree. Similarly, we'll repeat it for the ancestor node 3 and similarly for the ancestor node 6 and so on. The time complexity of this would be O of n square because for each node we have to compare it with all the nodes in its child subtree. Let's try to optimize this. One thing to observe in this question is that for each node we are trying to maximize its absolute difference with all the nodes in its child subtree. And since we are trying to maximize this absolute difference, we are actually interested only in two values in the subtree. They are the minimum and the maximum values of the subtree. If you consider any other node which is greater than our ancestor node, for example 10, its absolute difference with the ancestor node would always be lesser than the absolute difference of the maximum with the ancestor node. Similarly, if we take any other node which is lesser than our ancestor node, for example 6, its absolute difference with the ancestor node would always be lesser than the absolute difference of the minimum with the ancestor node. If this part is a little unclear to you, you can plot the values of the ancestor node and all the values in its subtree on a number line, and you will notice that this property holds true. So we are only interested in two values from the subtree, the minimum and its maximum. Similarly, when the ancestor node is 3, its maximum difference can only be with the minimum of its subtree or the maximum of its subtree. Let's see if we can cut down some repetitive work. Let's see some properties of the maximum and the minimum of a subtree. For the subtree of 8, its maximum is going to be the maximum of 3 values. One of them will be its own value, and the other two will be the maximum of its left subtree and its right subtree. And similarly, its minimum is going to be the minimum of 3 values. One of these will be its own value, and the other two will be the minimum of its left and the right subtree. Similarly, the maximum of this subtree would be the max of 3 values, its own value which is 3, and the maximum of its left and the right subtree. Similarly, its minimum is going to be the minimum of 3 values, its own value, and the minimum of its left and the right subtree. For any leaf node, there are no left and right subtrees, hence its own value will be the maximum and the minimum. Similarly, for this subtree, the maximum and the minimum will be 13. This value can be reused when we are finding the maximum and the minimum of its parent. Since 14 does not have any right child, we'll only consider values from its left subtree. Similarly, we can use these values to find the maximum and the minimum of its parent. These values will be the maximum and the minimum of the right subtree of 8. Similarly, we'll find the maximum and the minimum for its left subtree. The maximum from the left subtree is 7 and the minimum is 1. And the maximum from the right subtree is 14 and the minimum is 10. So 14 will be the maximum of the entire subtree and 1 will be the minimum of the entire subtree. We'll find the difference of these two with the ancestor node, and whichever is the maximum, we'll compare it with the maximum difference we have seen so far, and if it is greater, we'll update our answer. So starting from each leaf node, we have to return two values, the minimum and the maximum of its subtree, and these values will be used by the parent node to calculate the minimum and the maximum of their subtrees. So we are calculating values from the bottom and using it to solve values for the top nodes. This approach is called as a bottom-up approach. This is commonly used to solve many types of problems such as binary trees, graphs, dynamic programming. Let's look at another approach to solve this same problem. Let's take a path-based approach in this problem. If we consider this path, the maximum value in this path is 8 and the minimum is 3. So the maximum possible difference would be 5. We can consider all the nodes in this path because as we are going down the path, the nodes will share the same ancestor. And as we are traversing down the path, we can keep a track of the maximum and the minimum found so far in this path. Similarly, the maximum and the minimum of this path would be 8 and 3, so the difference will remain unchanged. The maximum and minimum of this path would be 14 and 8, so the difference 6 would become the new maximum difference we have seen so far. And when we consider this path, the maximum would be 8 and the minimum is 1. The difference 7 would become the new maximum difference we have seen so far. And this will be our answer. So in this approach, we start from the top and pass two values, the minimum and the maximum of the path so far. These values are used by the child nodes to calculate the maximum and the minimum of their paths. And when we reach a null node, we find the absolute difference between the maximum and the minimum. And if it is greater than all the other differences, we update our answer. In this approach, we start with values at the top and pass these values to their children, which in turn use these values to compute their result. And these nodes themselves pass these values to their children and so on. Hence it is also called as a top-down approach. And since we have to pass values at the root node, we'll use plus infinity as the minimum so that when it is compared with the root node itself, it would become the minimum value in the path. And it is given in the problem statement that all the nodes are at least 0, so we can pass 0 as the maximum. Otherwise, we could have used minus infinity. So when it is compared with the root node, it would become the maximum in the path. The time complexity of both these approaches would be O of n because we have to go through all the nodes once. And the space complexity would be O of n stack memory because of the recursive call stack. Let's implement both these solutions. Let's start with the bottom-up approach. We can initialize our result to be 0. We'll have to write a DFS function which returns two things, the minimum and the maximum of that subtree. Firstly, we'll define our result variable to be non-local so that it can be used in this recursive function. We are interested in the value of the node itself and the minimum and the maximum of the left and the right subtree. So let's keep an array to store these 5 values so that the code will be easier. We'll initialize it with the current value. It is already given in the problem that the binary tree is non-empty, so we are not checking if it is a null node. We'll check if there is a left child, then we'll find the minimum and the maximum of it and add it to our array. So now we have stored the left minimum and the left maximum. We'll have to do the same thing if a right child exists. We'll call DFS on the right child and add the right minimum and the right maximum to the array. Our minimum and the maximum of this subtree will be the minimum of these 5 values and the maximum of these 5 values. We'll find the absolute difference of the current value with the minimum and the maximum, and if it is greater than the maximum difference we have seen so far, then we'll update our answer. At the end, we'll return the minimum and the maximum of this subtree. We'll now call DFS on our root node, and finally we'll return our answer. Now let's implement the top-down approach. Here we have to pass the minimum and the maximum of the path to the recursive function. So we'll add 2 more parameters. Our default value for the minimum would be infinity, and for the maximum it would be 0. Let's write our terminating condition when we reach a null node. In that case, we have to return the difference between the maximum and the minimum. We don't need an absolute function in this case because the maximum will at least be greater or equal to than the minimum. Our new minimum for the path would be the minimum of our current value and the minimum we have seen so far in the path. Similarly, the new maximum in the path would be the maximum of the current value and the maximum we have seen so far in this path. And finally, we have to pass the new minimum and maximum value to the left and the right child, and from whichever of these two paths we get the maximum difference, that difference would be our answer. So we'll call DFS on the left and the right child and return the maximum of it. We are now done with our solution. Let's submit it. As you can see, our solution is accepted. If you thought this video was helpful, please leave a like and subscribe to the channel for more such content. Thanks for watching.